Good morning. Welcome to NICE. So I will be talking today about how we use AI to improve customer service. But first, let me tell you about what customer experience is all about, what we are doing here. So, thanks. Customer interaction with the company starts when the customer first accesses the website of the company, fills in a form, or initiates chatbot application. So all this information can be collected, and if customer decides to talk to a live agent, we can use this information to route him to the most suitable agent. Our systems monitor the calls in real time and guide agents in terms of process that they need to fulfill, in terms of insights that we can get about the customers, and alert about actions that need to be done. Every interaction is recorded and analyzed for basically everything. Category, topic, intent, actions, events, sentiment, behaviors, everything is used for quality evaluation of agents and targeted coaching, and also for future planning in terms of forecasting and scheduling. We also focus on the customer side. We collect feedback, we extract insights from the conversations, and we visualize, analyze, and optimize customer journey. So as you can see, this is very rich world, rich with the opportunities to use AI to improve customer experience and customer service. I will show you three very different ideas from three very different areas. So let's start. Let's start with LLMs, probably the hottest topic these days. And we all know that LLMs disrupt customer experience. We talk about self-service and chatbots powered by LLMs. We are discussing how we can make our classification, intent extraction, summarization models better using LLMs. We are thinking how we can provide agents information in real time using LLMs, and how we can use LLMs for agent training and coaching. LLMs come with lots of issues these days. So context window could be a little bit short, not enough for some of the use cases. LLMs are slow, okay, and due to the model size, due to the service latency, and this is, well, we need to consider if they are suitable for real-time use cases. They're expensive. So NICE records 7.7 million interactions per day, okay, in the cloud. So think how much money we need to pay for it. Okay, LLMs are sensitive to prompt. We need to install guardrails to protect LLMs from prompt injection and all the legal and compliance issues that we need to deal with. But let's say we solved it all. Okay, we know how to handle it, and what we want to do, we want to implement conversational chatbot that can offload some of the work from real agents. Okay, so building such a chatbot is a very hard task. First, we need to connect it to internal knowledge bases, internet, give it all the internal information. Well, that's kind of solvable, but that's not it. Any service interaction has a structure. Okay, it has a greeting part, customer authentication, problem understanding, and resolution. And both need to be able to drive these structured conversations, sometimes not in a linear fashion. Bots need to understand and react to customer emotions, and bots also need to sort of control the conversation, set clear expectations, own the conversation, be proactive, but at the same time be empathetic. So that's kind of hard for a human agent as well. So this is why we have developed RTIG, which is real-time interaction guidance, basically a set of classification models that each of which is focusing on a specific behavioral aspect. These models monitor the calls in real time and alert agents if any change or adjustment is needed. Okay, so agent get these messages with recommendations. Do this, say that, be more empathetic. Okay, a similar idea can be used with chatbots. So what we can do, we can collect basically conversation history, send it to the real-time models, and if they produce sort of recommendation, we can inject them into the prompt of the chatbot, and this way control its behavior. Okay, so let's move to another area. Let's talk about simulations, and specifically simulations powered by machine learning. But first, I want to tell you a few words about workforce management. So workforce management, one of the biggest and most important products here at NICE, focuses basically on answering two basic questions. How many people do we need? And when do we need them? And we do that in 3 steps. First, forecasting call volumes and average call durations. This is usually done per skill, which is a combination of topic, language, channel. And so the next step will be compute how many people do we need with respect to the forecasted volumes in order to meet service requirements. And finally, the next step is scheduling, assigning real people to the shift, taking into account not only the calls, but also other activities, such as lunches, breaks, training meetings, and more. So all these issues are usually addressed using operational research technology, such as optimizations and simulations. So let's talk about simulations. Simulations are computer programs that model real-world systems. But basically, to build a simulation, we need to identify all the input parameters, all the features that affect the system. We need to describe their behavior and how they interact with each other. And then we can basically run the simulation and understand how systems are working under different conditions. So simulations are widely used for training, flight simulators and such, military, medicine, manufacturing, logistics, gaming, financial modeling, and more. In customer service, we mostly use it in workforce management, for example, to verify that recommended scheduling ensures that service requirements are met. Simulations are in many ways similar to machine learning models. They both have the same goal, predicting the output based on the system output based on some input parameters. These are different technologies, but if you analyze them, you see that they sort of complement each other. So for example, simulation, you need to identify all the moving parts, all the features, understand their behavior, describe it. While in machine learning, you just get a lot of data and just throw it in some machine learning algorithm and hope that it will learn the patterns. Sometimes there is advantage in that, specifically if we have many variables. Simulations can easily adapt to a change in the system. You just identify the parts that changed, change their behavior, and that's it. In machine learning, you will have to recollect the data, and you will have to retrain it. So, however, machine learning are fast, okay, while simulations are usually slow and time and resource intensive. So, combining these technologies could be a sorry. So combining these technologies could be a really good idea that could produce a system that is both effective and more efficient and resilient. There are many ways how we can combine these two technologies. The straightforward way is to use simulations to generate data. Okay, we can then use this data to train machine learning models. We call them surrogate models. In this example, a surrogate model learns to predict system output based on the input. And we can use both of these technologies together. We can first run the surrogate model. And if it's not certain enough in the result, we can go back, run the simulation, and even update the model with the new result. This example is very similar, but the surrogate model here learns the opposite relation. It learns to predict system, the input based on system output. This could be very useful if we want to find optimal parameters that satisfy some given requirements. In this case, we first run surrogate model, identify some initial point for search, and then we use simulations to sort of investigate the area around this initial point. Okay, so let's move to another example. Let's talk about how we can use causal discovery to automate root cause analysis. So meet Jeff. Jeff is an agent in a telecom company. He's a great agent, but in the last couple of weeks, it takes him more time to handle his conversations. His AHT, average handle time, goes up, which is bad. Okay, so what could be the reason for that? Any number of things, right? He could be, it could be personal issues that cause him to be less concentrated on the calls, and consequently, talk time goes up, AHT goes up, and maybe in this case, we need to talk with Jeff. Just ask him what's going on, and sort of that talk. But it could be some knowledge gap. A new product, new service was introduced in the last couple of weeks, and Jeff wasn't trained on it. So he uses knowledge base a lot. We see lots of silence in the calls, and that basically what causes the long duration of the call. However, it also could be that in the last couple of weeks, Jeff handles more complex calls, meaning that billing calls, for example, take longer to complete. So there's no problem. It's just a different distribution of the topics. So in order to pick the right corrective action, we need to understand which one of these hypotheses is correct, and for this we need data. Our products provide some of this data in the form of charts, in the form of dashboards, but still this is a lengthy manual process that we would like to automate. So one way to automate this could be using causal discovery technology, or specifically causal graphs. Causal graphs, or DAGs, direct acyclic graphs, their nodes represent features, and edges represent causal relations. So in this example that you can see here, AHT is directly dependent on silence time and talk time in the conversation, and the talk time itself depends on the topic, in this case, let's say billing, and agent concentration measured by a listen actively metric in this case. Causal graphs have also probabilistic interpretation and functional representation. So in functional representation, each feature basically defined as a function of its parents and some residual that basically represents the contribution of the feature itself. So for example, talk time is a function of billing and listen actively, but it also has a component that is part of the talk time itself. That's the epsilon. So one of the biggest issues in constructing causal graphs is how we break symmetry. If we have two variables, X and Y, and both of them are correlated. It could be that X causes Y, Y causes X, so there is a confounder, right, that affects both of them. So how we can know which is which, and there are a couple of tricks that people use. One of them is conditional independence test, used in algorithms such as PC or FCI. Another idea is to use scores, for example, entropy. So the motivation here is that if we have a graph with correct causal relations, it will have lower entropy than graph with incorrect causal relations. Another option is to assume or explore exploit certain characteristics of the data. For example, assume that the data is non-Gaussian. So one algorithm that does that, called Lingam, linear non-Gaussian cyclic model, it also assumes that the function that describes causal relations between the feature and its parents is linear. Let's see how this trick helps to break the symmetry. Okay, so let's look at the bottom line first. Okay, the data here is uniform, so non-Gaussian, right? So what we can do, we can train two regressions, X and Y, Y and X, and for each case, we can calculate the residual, epsilon, and measure the level of dependence between the epsilon and the exploratory variable. So we can see that epsilon is independent of X on the left, and on the right, epsilon is dependent on Y. So the correct causal relation here is that X causes Y, right? And in the top line, we see that this trick doesn't work because the data is Gaussian. So this slide kind of summarizes the logic behind Lingam. I'll skip it because it's basically trivial. And this is my last slide. So if we have a causal graph, what we can do, we can use data to measure the impact of each factor on the target variable. And if we compare how this impact changed over time by comparing, let's say, historical data set and the new data set, we can identify the factor that basically caused the change in the target variable. Okay, hence the root cause, and this is how we'll do root cause analysis.